All right, advanced placement calculus. How you doing out there? Happy Monday. Hope everybody had a good vacation, holiday. I usually start these out with some music, but my wife's been doing YouTube videos as well, and she had a couple that were blocked because the music that she used was copyrighted. So I'm afraid to use music now, and that they're going to block my video, and I'm going to have to do it all over. Who knows, at some point I'll probably get music going on again. Don't forget that differential equation, take-home quest is due today. It's your last grade of the third quarter. This would be Monday. We started AP review. Hopefully you got a chance to look at 2008, section 1, part A. This is part B right here. Part A was non-calculator. I know the instructional video is a little bit long, okay, but you should have spread that out over 3 days right there. We'll do part B. Part B is the graphing calculator part. All right, 17 questions here we're going to do. The new AP has only 15, but once again, for your AP, you're not going to have multiple choice anyway. But look, still important to review this stuff, if not only for next year, if on your free response questions, they actually, tack a bunch of multiple choice questions in there or something like that, would not be surprised. Some of these are extremely easy. Some of them are extremely difficult. Remember, if you want to get a 3, you're really supposed to be averaging about 4 out of 10 problems right. If you want to get a 5, you're supposed to be averaging about 7 out of 10 problems. So you're not supposed to get everything right on the AP exam. The important thing is to keep working, okay? Keep yourself confident, okay? Fight your way through this stuff. You'd be surprised how much you actually know and that you could do. I know a lot of you guys have problems with confidence. You shouldn't, okay? You're going to be a lot more prepared than a lot of other people taking this truncated AP that you're going to be taking. They give you the graphing calculator here, but you'll notice it's really only useful for a few of the problems. Here, it's completely useless. Number 76, that's Mr. Harrington's age. They give you the graph of f prime. The derivative f is shown above. On what intervals is f increasing? Oh, f increasing. Surely there must be some sort of test. And there is the first derivative test. Okay, you could draw that f prime line, right? But you're telling me I want to draw the line for the graph that I'm given. It's right there. I check above and below. We go from -2 up to 5. You'll see that it's above until you get to 1, and then it's above again until you get to 3. And then below until you get to 5. Here at 1 and 3, those are places where the derivative equals 0. Doesn't matter in this problem, but it could matter in other problems where you want maxes or mins. So where is f increasing? When f prime is positive, right? When the slope of f is positive, that happens from -2 to 1, and then from 1 to 3, okay? Now, if you want, you could just say -2 to 3, which is what they're looking for. You can increase when your derivative is equal to 0. That's okay. They'll never have the 2 separate intervals and this one interval. They'll either have one or the other. So hopefully that problem right there is pretty easy. Just like 77 should be easy. Which of the following statements are true about f right here? Domain 0 to 4. The limit as x approaches 2 from the left-hand side exists. I know it's been a while since we did limits, but remember, limits are all about where you're going, not where you get to. And if you approach 2 from the left-hand side, go to the left to 2, find the function, move to the right, you'll see you're approaching that dot right there. You don't get to that dot, but whatever the heck the y value is, that's the limit. There is a left-handed limit, and there's a right-handed limit. As you go to the right of 2, you move to the left, you'll see you're approaching that dot right there. Who cares if he's open or solid? He still has a y value. This y value right there, that's going to be the right-handed limit. They both exist, okay? It's just that the two-sided limit means the left-handed limit has to equal the right-handed limit. Not true here. Here's the left-handed limit, this y value. Here's the right-handed limit, that y value right there. So we can see that this is a might as well jump discontinuity, okay? And the limit never exists at a, jump discontinuity. So be careful with something like that. Should be pretty easy to do. 78, calculator classic here. The first derivative function is given by f prime equal to this. On what intervals is f increasing? What's that feeling? You can only say what is in French. Deja vu, okay? We just did a problem like this. F is increasing when f prime is positive. It could also increase when f prime equals 0 or non-existent. People are like, well, I want to draw the f prime line. Is it bounded? It is, from 0 to 2. But people are like, well, I don't have the graph of f prime. How do I do it? Well, we can get the graph of f prime, okay? Take your trusty, hopefully not too dusty, graphing calculator, radian mode, okay? And graph this thing, sine of, we have the quantity x cubed minus x. Definitely zoom fit here, right? They tell you from 0 up to 2, little zoom 0 action. And look, here's the graph of f prime. Are you telling me I want to draw the line for the graph that I'm given? It's when you check above and below. And you can see this thing starts out above. It starts out below. What am I thinking here? Then it's going to be above. and then it's going to be below. Okay, so we want to know in the intervals where this thing is actually increasing. So where is f prime positive? You can see it starts right there at 1. Calculate the 0 if you're not so sure. Calculating the other 0 over here, little bug action, a bug. And you can see we got 1.691 approximately. Okay, so you can see that f prime is positive from 1 up to 1.691. Looks like my answer right there is B. I'm sure you're all very happy. I got a printer on my hands. I fixed my printer, so we have the dittos right here. So hopefully the first 3 problems really not too terrible. The next one's not bad either. Okay, they tell you if this definite integral from -5 to 2 of f of x is -17, and the integral from 5 to 2 of f of x with respect to x is -4, they wanted the value of this integral right here. Remember, you can split every single integral into multiple integrals. We usually only split them into 2. Okay, so the first integral is going to start at the lower bound, and the second integral is going to end at the upper bound. Remember, you can do this with any integral you want as long as you put the same number here as you put here, and it doesn't need to be a number in between -5 and 5. You could put a 60 here, as long as you put a 60 here. Now, this is an easier problem because you see we're putting a 2 here and here because that's the other number they gave us. But, you know, just to think about it, they might ask next time the integral from -5 to 2, not -5 to 5. You could split the integral from -5 to 2 over 5, even though 5 isn't in between -5 and 2. Anyway, the integral from -2 to -5 to 2 of f of x we know is equal to -17. Plus, just remember, the integral from 2 to 5, well, if the integral from 5 to 2 is -4, that means the integral from 2 to 5 going to be +4. Okay, stuff that we spoke about in here already this year, and we know that's a -13. Remember, if you integrate backward, it's going to change the sign of your integral. You know, another way to look at it is that you could negate both sides. Or how about not negate both sides? How about this? How about swap the bounds, right? If you want to swap the bounds, you could do that as long as you put a negative in front. Just remember, it's still equal to -4 right here because this side is equivalent to this side. Now you can multiply both sides by -1 and get that the integral from 2 to 5 of f of x with respect to x, I don't know why I'm putting that there, is equal to +4. Okay, so look, you could do it that way as well. I think it's easier to just realize when you switch the direction you're integrating in, you want to, take the opposite of your answer. Really up to you. The derivative of the function f in number 80 is given by f prime equal to this right here. How many points of inflection does the graph of f have on the interval -2 to 2? Points of inflection, I mean, surely there must be some sort of test. And there is, okay, the f double prime line here, if you want to know where f has points of inflection. We know it's bounded from -2 to 2. Calculator situation here, right? They give you f prime. Okay, so if we graph f prime, we got x squared, cosine of x squared. Make sure you're in radian mode once again. Hey, she came in through the bathroom window. Make sure if you zoom fit, which you should do here when they give you an interval, make sure you put the interval in first. Little zoom fit action. And be careful now, we're not looking at the graph of f double prime. This is the graph of f prime, okay? And are you telling me I want to draw the line for the derivative of the graph that we're given? That's when you check slope, increasing and decreasing. You can see this thing starts its life by decreasing here. So f prime decreases, which means f double prime is negative. Then it increases until you get to this max, and then it decreases until you get to 0. Okay, then you can see after that it's going to increase. Then it's going to decrease until you get to this min. Then it's going to increase again. Okay, you don't need to calculate these values. They just want to know how many points of inflection. That's when f double prime changes sign. Happens 1, a 2, a 3, 4, 5 times right here. Okay, so just be careful. Remember, if you want to draw the line for the graph that you're given, that's when you check above and below. You want to draw the line for the derivative of the graph that you're given, because this graph over here was f prime. Then you check increasing and decreasing. You check slope. Really, not a bad part B so far, so I'm sure some filthy problems are coming. You might consider 81 to be a little bit of a filthy problem here. You know, here they tell you that g of x is an antiderivative for f of x. Remember what an antiderivative is? An integral. So g of x is an integral for f of x. So if you actually integrate f of x, with respect to x obviously, you get big g of x back. Okay, that's what that means. And remember, that's somebody's derivative in there. Whose derivative? The answer's derivative. So if you take the derivative of g you're going to get back f, okay? You know, that's what that really means. Not so easy to realize. You know, here they actually tell us an initial value for g. Then they want g evaluated at some other x value. And remember, if they give you a function evaluated at some x value and the rate at which the function changes, you can get the function evaluated at any x value you want. You know, there are a lot of different ways to do this problem, but the easiest way is to use the fundamental theorem of calculus. And what I mean is if you want g of 4, start with g of something else. They gave us g of 2. But you want to add to that the change in g. You want to know how the heck did g change from x equals 2 to x equals 4. That's why we integrate from 2 to 4. And if you want that change in g, you integrate the rate at which g changes. Because think about it, if you integrate g prime, you get back g. And you're just going to do g of 4 minus g of 2. That's the change in g from x equals 4 to x equals 2. You're going to add that change to g at x equals 2 to give you your answer. G of 2 we know is -7, plus the integral we know it's 2 of 4 here. Instead of g prime of x, you could say f of x. And they actually don't want the answer. They actually want to know the representation for the answer, the integral representation. And you can see it's right here, okay? They use t instead of x. They just use the dummy variable. Nothing wrong with that. If you wanted to define a function that would give you g at any x value, you'd start with g of 2. You'd add to that the change in g from 2 to x, and if you put an x up here, then you can't put f of x inside here. You got to use f of t. So that's why they're actually doing something like that. Not that you need to know for this particular problem, but it's really just a dummy variable, really just a pushy variable, like we said before. So that one's tricky right there, not so easy. Make sure you look at your solutions and see the percentage you got these problems right. It's probably pretty low for 81 right there. It should be high for 82 though. You know, they tell you particle moves along a straight line. They give you velocity function right here. What's the acceleration at t equals 3? Well, a of 3 is equal to, you know, what do you do to velocity to acceleration? Take a derivative. It's equal to v prime of 3. You could differentiate this. Not so easy because it's an a to the u right here, so it would probably bother people. I wouldn't differentiate it. Remember, if you have your calculator, you can numerically evaluate a derivative on the AP exam. So let's put in... okay, this velocity function right here. Okay, now I could actually do a little math 8 action. Had a dog named Math. I fed him math 8. Let's take the derivative with respect to x of the velocity function, alpha twaithy, y1, and evaluate him at x equals 3. I do that, and I get approximately 0.055. If you round, if you truncate, you get 0.054, which is not here. So the moral of the story is, if you truncate, you're going to lose the AP exam. Anyway, just kidding. Okay, obviously, they won't give you a rounded and a truncated result. I've really only seen rounded results in multiple choice. Wonder if they give you truncated results. I haven't really seen it. Doesn't mean it doesn't happen. So that one right there, hopefully not too terrible. 83 is not bad either, but 83 is a real time waster here. You know, the area bounded by these two curves. You know, you're thinking about an upper minus lower here, and you burn a lot of time just actually graphing this thing. Okay, putting it in the calculator. Have a care. Okay, make sure that you don't, mess up putting it in the calculator. I could be messing up right now. You're watching the video like he's messing up. He doesn't know. I don't know, maybe. You know, if you zoom 6, something like this, you could try zooming 4. I think it's a little bit too small. If you zoom 6, it gives you a decent window. Okay, and it looks, I don't know, a little something like this right here, and then we have y equals x cubed, yada, yada, yada. And this guy right here, just want to make sure I do this correctly. I think that's pretty good, right? Here's y equals x plus 5. You can see how annoying it is, right? 2 regions, you got to do 2 upper minus lowers, okay? You're going to have to calculate here, maybe make this b, make this intersection C, make this D over here. So my area is going to equal, when you draw that rectangle over here, you could see that upper minus lower is going to work from B to C. So the integral from B to C. Upper function minus lower function. Upper here is the cubic. So x cubed minus 8x squared plus 18x minus 5. Minus the lower function, which is the linear. You'd have to put it in parentheses. Okay, plus, now this next integral is going to go from C to D. Now the upper is the linear minus the cubic. I wonder if I'm going off the paper there. It looks like I am. Okay, minus the cubic, all with respect to x. And the thing is, you got to calculate these intersect points, okay? You know, it's a part one, so I don't have to worry about writing all the work down perfectly. But if I calculate my intersect, that guy's actually 1. Maybe they're all nice, right? Maybe this is a 1 right here. They're probably all nice. Sometimes they're not, and they really end up making it difficult to do a problem like this because it is time consuming. But it looks like they're being pretty nice with this one, right? We're going to go from 1 to 2, then here from 2 up to D, which hopefully is going to be something nice as well. I've seen problems like this where they're pretty filthy bounds, and it's almost, this would be a 5 right here, it's almost worth skipping the problem because you could burn so much time by actually calculating the bounds. Don't have to worry about that here, okay? But sometimes, you know, they kind of mess with you and they want you to make a decision. This is an easy problem, but it's time consuming. Do I want to spend time on it? Things like that. My cubic is Y1, so low math 9er. Nothing could be finer. All right, integral from 1 to 2. My cubic is Y1, so alpha twaithy, Y1 minus alpha twaithy, Y2 with respect to X. Plus this other integral, math 9er from 2 to 5. Well, 2 to 5er. Nothing could be 5er. Why don't you don't put the 2 in there, man? What's up with this calculator? And then we got Y2 minus Y1. With respect to X. Hit enter, and I get 11.833 approximately, which you can see is answer choice B. Newsflash, on your AP, they say area between two curves is not going to be on there. So you probably won't have to worry about this type of problem right here. But once again, we'll focus more on exactly what's going to be on your AP toward the end of the review. Want to make sure you get a good review in beforehand. So actually a pretty easy problem, number 83, but you could burn some time with it. 84 is actually really easy. They give you the graph of the derivative function f. Make sure you read these things as shown above. Horizontal tangent lines at x equals -1, x equals +1, and x equals +3. Okay, which of the following values of x does f have a relative maximum? Well, surely there must be some sort of test, okay? And that's the f prime line. We know it's bounded here from -3 to 5. Are you telling me you wish that I draw the line for the graph that I'm given? Because that's when I check above and below. And you can see below until you get to -2. You can see above until you get to 1. Then above again, right, until you get to 4. Then below. And at -2, 1, and 4, those are all places where f prime equals 0. Well, horizontal tangent action. We're looking for the max, okay? It's not at -2. It's not at 1. It's at +4, okay? You know, and you could do it just by looking at the graph. Come on. F has a relative maximum when f prime equals 0 and changes from positive to negative. We should know about that. You got to know about those justifications. Part 2 problems coming tomorrow. You know, and that means that, look, f prime equals 0 changes from positive to negative. Here's f prime. Function always represents y values. So the y values equal 0 right here, and the y values change from positive to negative. So you could do the problem without even drawing the line, but the line doesn't really take too much time to do. It's really not too terrible to do. Number 85. 85, the year Marty McFly traveled back in time. The table above gives a function f and its derivative. Okay, it's selected values of x, so a function represented tably. F prime is continuous, which is nice. If f prime is continuous, it actually means that f is differentiable, okay? Not something I really talk about a lot, but f prime is continuous. The reason they're saying it's continuous is because you have to perform a definite integral on it. It's the area between a function and the x-axis, or the opposite of the area. We know integrals can be negative, but the function's got to be continuous in order for you to do that. So that's really why they're telling you that. They don't really mess with you and tell you it's not continuous, and then you have to write the integral doesn't exist. That's not what you really see. In those cases, you got to split up integrals. We'll talk about that when we need to. People look at this, they think it's so difficult. It's the easiest thing in the world. People are like, I can't integrate f prime of x. Well, come on. That's somebody's derivative in there. I wonder what you have to take the derivative of to get f prime of x. How about f of x? Now we evaluate him from -4 to -1. Just don't forget that means plug in the upper bound, subtract the plugging in of the lower bound, okay? And f of -1, make sure you look at the f chart, minus f of -4, which is 0.75. All right, look, hey, if you're scared to subtract these, you got a calculator. It's the calculator section. I'm not cheating here. I can use this. Okay, so -2.25. Do something like that if you need to on the calculator section. I think on your AP they said you're not going to really need a calculator, but keep it close by. You know, we'll talk about that more as we go through. So 85 is supposed to be easy. 86 is also easy. It's a little bit weird. Another function represented tably, velocity. Selected values of velocity. always be careful with a function represented tably. You know, they didn't tell you velocity was polynomial or that it was continuous. So there could be all kinds of weird things happening in between these values. But we do know at t equals 0, the particle's at the origin. That's actually an initial dish right there. Okay, so when t is equal to 0, x has got to be equal to 0. And they want to know which of the following could be the graph of position. Well, you could use this initial dish, okay? You know, x of 0 is equal to 0 for AC and also E down here. But position at t equals 0 right here is -1. That's not right in B. And it's equal to -1 in D as well. Probably because a lot of people are looking at this, right? You know, V of 0 is -1. That's the initial slope of position, not the initial position. The easiest way to do it is this. At t equals 3, velocity is 0. Remember, if velocity equals 0, that means the derivative position equals 0, which means the position function is going to have a horizontal tangent line at t equals 3. And you can see that doesn't happen in A over here. Here's t equals 3. That's not a horizontal tangent line. At C at t equals 3, looks pretty good, right? Horizontal tangent line. E at t equals 3, the horizontal tangent's actually a little bit to the right. But even if you're a little freaked out by that, you're like, wait, maybe that's right. Look at this up here. One last thing. Between t equals 0 and t equals 1, velocity changes from negative to positive, okay? Which means that the slope of position must change from negative to positive. Position must change from decreasing to increasing somewhere in between 0 and 1. That happens here. In between 0 and 1, position changes from decreasing to increasing. Here, between 0 and 1, position's only decreasing, okay? So the velocity would actually always be negative. So be careful, okay? That's why C is the answer. But I really think you can do it just because of this information over here. Sometimes you don't need to overthink AP problems. Sometimes you do, but not really in this situation. 87 is actually also supposed to be easy if you know about the fundamental theorem. An object, is it a particle? I don't know. It's an object. An object, can we say that in British? A British object traveling in a straight line has position x of t at time t. Initial position right here. And they give you the velocity of the object. And they want to know the position of the object at t equals 3. So we want x of 3. And you might remember we did a problem like this in the non-calculator part. And you were able to just integrate velocity, okay, and then actually be able to solve for C and then get what your position function is and plug in there. But we did it both ways. We did it with the fundamental theorem of calculus, and we did it by just integrating velocity, because this is not integratable, okay? 1 plus t squared, quantity to the 1/3 power. It's not something we know how to integrate in here. So look, you got to use the fundamental theorem. And remember, if you want position at any t value, as long as you have position at some other t value and the rate at which position changes, that means you can get position at any t value you want. So start with position at t equals 0. Then say to yourself, hey, what the heck was the change in position? How did position change from 0 up to 3? And if you want that change in position, integrate the rate at which position changes. Okay, we talked about that before. Some people go right to saying, hey, the initial position is 2 at t equals 0. To get change in position, we just integrate velocity, right? Because that's displacement, change in position. I like to start this way because if it's more abstract or applied, you're going to have to think about it that way. But you can go right here if you want to. And look, now you could use the calculator because you could use the calculator for a definite integral. You know, if you look at the success rate for the problem we did on the section A that was similar to this problem, you'll see it was pretty high. I think it might have been like the 60s or maybe even the 70s. But if you look at this rate, you'll see that it's actually much lower because people don't know the fundamental theorem on the AP exam. And it's the most important formula for you to know. Really would not be surprised if it showed up on one of the section 2 problems you're going to have. Anyway, I could pop this all in my calculator. 2 plus, little math niner. Math 9, 0 to 3, alpha 2 y1 with respect to x. And I get 6.512. So you can see they round as well. So truncators get lost, okay? 87, a problem you can do. And I know at first you're like, I don't remember this stuff. What's going on? I'm going to fail the AP. No, relax. You got to get yourself into the AP groove. We're doing a lot of review. They extended when the AP is going to be. So we're going to have so many problems. AP problems are going to be doing. By the time we get there, you will feel prepared. I hope. Maybe I'm just saying that. I'm just kidding. 88, the speed required to travel through time. A lot of Back to the Future references here. The radius of a sphere. is decreasing at a rate of 2 centimeters per second. At the instant when the radius of the sphere is 3 centimeters, what is the rate of change in square meters per second of the surface area of the sphere? And they give you formulas for the surface area. And I don't know if you remember what kind of problem this is, but they give us a rate, the radius of a sphere, decreasing at a rate of 2 centimeters per second. They ask for a rate, okay? They want to know the rate of change of the surface area of the sphere, and they indicate a specific instant, right? When the radius is 3 centimeters. That's a related rate problem. I don't know if you remember that, but we're talking about a sphere here. And you're usually supposed to try to draw a diagram for related rates, but for a sphere, it's really silly because it only has that one linear measurement. It's never constant. Nothing can ever be constant with the sphere. Here they say that this radius is decreasing with 2 centimeters per second. Okay, so that means the rate at which the radius is changing with respect to time, dr over dt. If you just put 2 centimeters per second, you're wrong, okay? Because this thing is getting smaller, and if something's getting smaller, its rate of change is negative. So just be careful. What do they want? Well, they want the rate at which the surface area is changing, right? So ds over dt. They don't say the rate at which the surface area is getting smaller. We know the surface area is getting smaller, right? Because the radius is getting smaller. They want the rate of change of the surface area. Surface area is getting smaller. The rate of change could be negative. All the answers are negative. They could have made it a lot more difficult by putting some positive answers in there, just so you know. What's the instant, by the way, when r is equal to 3 centimeters? Okay, so look, you need a formula that relates the variables. They give it to you, s equals 4 pi r squared. But we want to turn an s into a ds over dt. Differentiate implicitly with respect to t. The derivative of s with respect to t is ds over dt. 4 pi is a constant. Pull it to the side. Drop the 2 down. Okay, 2 times 4 pi, 8 pi. I was hungry, sorry, 8 pi. Raise r to the 1 less. Then multiply by the derivative of r with respect to t. Little chain rule action. Be careful. If you forget that, it's possible the incorrect answer is up here. It's negative, but you might still end up picking it anyway. Now we've actually stopped time. Sorry, silly little joke. We want ds over dt. We know that 8 and pi are constants. At this particular moment, r is 3. I can plug that in right there because I stopped time. dr over dt is negative 2. And now, what is that? Negative 6 times 8, negative 48 pi. All right, so I had a dog named negative 40. I fed him pi, negative 48 pi. If you had this as positive 2, you would have got positive 48 pi. If that was up here, this would be a more difficult problem. Okay, so things to think about. Not the worst part B so far. Until you get to number 89. In fact, 3 of the last 4 questions are pretty tough. 89, this is rough right here. If you're like, what the heck is the man doing? Da-da-da-da-da. Try not to worry so much. It might be a chalk it up as an L problem. But let's talk about it. The function f is continuous. From negative 2 to 2, they tell you f of negative 2, they tell you f of 2, they tell you it's 0. Then they tell you there's no c from negative 2 to 2, for which f prime of c is equal to 0. Which of the following statements must be true? And look, this is actually really a mean value theorem problem in disguise. If they want to actually tell you that there has to be some c value where a slope is equal to something. Remember the mean value theorem? If a function is continuous and differentiable, so mean value theorem, a function has to be continuous and differentiable. And that means that if that's true, if you draw the function, okay, and that just means that there has to be a place where the slope of the tangent line equals the slope of the secant line from one point to another. So if you go from this point to this point, here's my secant line. If the function is continuous and differentiable, there's got to be a place here where the slope of the tangent line is equal to the slope of the secant line. It looks like it would happen somewhere around there, where the instantaneous rate of change equals the average rate of change. That's kind of what this problem is about here. There are other value theorems to think about. The extreme value theorem, which means on a closed interval, if a function is continuous, it's going to have a max and a min. And also the intermediate value theorem, which means if a function is continuous in a closed interval, it's got to take on every y value from one y value to another y value. Anyway, so we'll start here by just sketching a little bit. Can't sketch much, right? They actually tell you here that this function has negative 2 comma 0 is a point, and also 2 comma 0 is a point. That's all they tell you. They tell you the function is continuous, okay? They want to know which of the following statements must be true, which means the other statements could be true, okay? But this one has to be true right here. So they're saying now from negative 2 to 2 that f prime of a constant has to be positive. So really they're trying to tell you that, this is the graph of f here. They're trying to tell you from negative 2 to 2, f always has to have a positive slope. That's impossible. To get from here to here, you'd have to either increase to decrease or decrease to increase or remain constant. See, slope does not have to be positive. It's impossible for that to be true for the entire interval right there. Then they're telling you for B, the slope always has to be negative to get from here to here. It's impossible. Now they're telling you, they're also telling you, remember, there is no C, for which f prime of C is equal to 0. The slope of the secant line right here, by the way, which would really be f of B minus f of A over B minus A, which in this case is really going to be, f of B minus f of A. So 0 minus 0 over 2 minus negative 2. You can see the slope is 0 right there. That's the slope of the secant line. Now they're saying which of the following statements must be true right here. Remember, they said there is no C, no place where the slope of the tangent line is equal to that slope of that secant line. So really, they're trying to say the mean value theorem is going to fail. Anyway, they're saying from negative 2 to 2 that f prime of k exists. If it did exist, that would mean that the derivative always exists from negative 2 to 2. That would mean f is differentiable. But if f was differentiable, then there would be a place where the slope of the tangent line is equal to the slope of the secant line. And the slope of the secant line here is 0. And they're telling you the slope of the tangent line is never equal to 0. So they're actually essentially telling you the function is not differentiable. In part D right here, they're trying to tell you the derivative does exist, but it's not continuous. But they're still telling you the function is differentiable. Here, if the mean value theorem is going to fail, then one of the criteria has to fail. The function either has to not be continuous or not be differentiable. We know it's continuous, so it must not be differentiable. Hence, the derivative does not exist between negative 2 and 2. Tricky question here. Believe it or not, it's actually Rolle's theorem. Rolle's theorem, if you want to talk about the mean value theorem, that was where f prime of C was equal to f of B minus f of A over B minus A. So f prime of C right there. And they told us that we knew the slope of the secant line here was 0. They told us the slope of the tangent line can never equal 0. There is no C. So that's why the mean value theorem had to fail. It's actually Rolle's theorem. Rolle's theorem is when f of A equals f of B, which happened here, right? Okay, and if that's true, besides being continuous and differentiable, also f of A equals f of B, that means the slope of the tangent line would have to equal 0 because the slope of the secant line would equal 0 here. So really it's Rolle's in disguise, even though they just really want you to know that for the slope of the tangent line to equal the slope of the secant line, function has to be continuous and differentiable. Here it was continuous, so if this isn't true, must not be differentiable. People are like, well, how could that happen? If it's going to get from here to here, it's got to look like that. It could do this. Now there's no place where the slope of the tangent line is equal to 0. Food for thought. And once again, tough problem, 89. Try not to freak about it. 90 is not so easy, but we've talked about it before, kind of. They tell you the function f is continuous in the closed interval 2 to 4 and twice differentiable in the open interval 2 to 4. When they tell you function's continuous and differentiable, you should be smelling the mean value theorem there, okay? It doesn't mean it's going to happen, but it's possible. Then they actually tell you the slope of a tangent line, which is interesting. Remember the mean value theorem? F prime of C has to equal f of B minus f of A over B minus A at least one time on the interval if the function is continuous and differentiable. So this has got to be true. This slope of the secant line's got to equal 2 at some place on this interval between 2 and 4. Anyway, then they tell you f double prime is negative, which means f is conc down. And remember, concavity is the rate of change of the slopes. And if the rate of change of the slopes is negative, that means the slopes are getting smaller. Mother, the slopes are getting smaller again. A lot of times they actually just, tell you if a first derivative is positive or negative, means the function is increasing or decreasing. They didn't do that here, okay? You got to see that the slopes are getting smaller, and we talked about it earlier in the year. If you go from 2 to 3 and you calculate the slope, 5 minus 2.5 over 3 minus 2, you get 2.5. And if you calculate the slope here, 6.5 minus 5 over 4 minus 3, you get 1.5. The slopes are getting smaller here, okay? F is concave down. So that's actually pretty good right there. That's a possibility. You don't need to really divide by the subtraction of the x values because it's just equal to 1. So if you look at part B over here, if you go from 2 to 3, your y values went up by 2.5. You do 5 minus 2.5 over 3 minus 2, you're going to get 2.5. And then you can see from 5 to 7, you're going to get 2. So that's also slopes getting smaller. So F is concave down. So he's in the running. C over here, you'll notice the slope is 2 from 2 to 3, and then from 3 to 4, the slope is 1.5. Once again, slope's getting smaller, so F is concave down. Man, hopefully here it'll change, and it does. In D, the slope is 2, and then again the slope is 2. That slope remains constant. That means F has no concavity. F is linear, constant slope, right? And here in part E, so he's no good. Part E, the slope is 1.5, then the slope is 2.5. Okay, so here the slopes are getting bigger. So F is concave up, which I'm not interested in. You know, the problem is, you're like, okay, I've narrowed it down to A, B, and C. Slopes are getting smaller for all of them. This F prime of 3 equal to 2. Try to think the mean value theorem. You know, there should be a place where F prime of 3 is equal to F of B minus F of A over B minus A. F prime of 3 was equal to 2. A to B, look, it doesn't need to be from 2 to 4. It works that way for all of these here, but it could just be from somewhere from 2 to 3, somewhere from 3 to 4. You should always try to actually use the two endpoints first, because usually that's what it is. So F of 4 minus F of 2 over 4 minus 2. You'll see it works for this problem right here, I think. Let's see. 6.5 minus 2.5, that's going to be 4 divided by 2 is going to be equal to 2. So it works for part A, the mean value theorem. Over here, if you do 7 minus 2.5, that's going to give you what? 4.5. And if you divide that by 2, you're not getting your 2 over here. And over here, 6.5 minus 3 is going to give you what? 3.5 divided by 2. You're not getting that slope of 2. So still a tough problem. 89 and 90, probably the two toughest problems on this part B for sure. But don't be like, oh, forget it, I can't do anything. You might be skipping those problems. I'd always tell people to guess. You know, you should answer every problem in the AP, even though you won't have multiple choice. But 91, just because you couldn't do the other ones, it's a piece of cake, okay? Average value of a function 1 over b minus a times the integral from a to b of whatever the heck you want the average value of. And they want the average value of this function right here. They're not asking you for anything strange, okay? What's the average y value this function takes on from -1 to 3? So that's 1 over 3 minus -1 times the integral from -1 to 3 of this guy right here with respect to x. And it's a straight up calculator type of situation. You know, while I'm putting this in here, a little alpha y equals fasciques, what is that, 1/4 right there? On your AP exam, there's not going to be average value. That's what they said, okay? So it's not actually in there. Too bad if you're going to get a problem like this because it's easy, but some of them are pretty tough, okay? So it's not the worst thing in the world to not have it on there. But once again, you might be like, why are we reviewing it? Because I want to make sure you remember all the things that we talked about this year, or at least get a review on them, because you will be in college next year. This whole coronavirus thing will be done, and you'll have to worry about stuff then, okay? So I want to make sure you know what's going on. I get 0.183, biggity bam, there it is. We got one more problem to do, okay? It's not easy. Number 92. Was that Toronto Blue Jays winning the World Series? I think so. Didn't they win in 92 and 93? Little Roger Clemens. Roger Clemens was there. Paul Molitor. Does anybody know these people? Anyway, so a city located beside a river, is there a van down by the river? Probably. Has a rectangular boundary as shown in the figure above. There's our city, rectangular city. The population density of the city at any point along a strip x miles from the river's edge is f of x persons per square mile. It's population density right there. Which of the following gives the population of the city? It's not so easy to do, okay? But you got to understand that the population density of the city at any point along a strip x miles from the river's edge, okay? So here's the river's edge. Then you're going to go out x miles, however far that happens to be, anywhere from here to here. So that could be x equal to 0 all the way up to x equal to 4, right? Population density is persons per square mile. If you integrate persons per square mile, you know, if you integrate the rate at which the amount of people are changing, you get the change in the amount of people. If you integrate persons per square mile, you get back persons, okay? So that's what we actually want as far as the population is concerned. So you want to integrate that f of x that represents persons per square mile. Integrate persons per square mile, you'll get back the amount of persons. What about bounds? Well, you could see, you know, x could be 0 all the way up to 4. So that's the integral from 0 to 4. Now, be careful. That answer is there, but it's not the correct answer because that's only the population along one strip. It's kind of silly to draw it as just a horizontal line because it is square miles, right? So this actually represents a square mile right there, so it's thicker. It's the amount of people right there. That's this integral. Remember, 7 square miles altogether. So if you really draw 7 of these strips, that's really what's happening. So you want to multiply this by 7, and that's going to give you your population right there. Still pretty difficult, not so easy to understand. So I don't know if I'm going to have this split up over Monday and Tuesday or just be the work for Monday. Might split it up because we do have a lot of review time. But we'll see what we're going to do, okay? Because that's technically 5 days in a part 1. Usually you could do it in 3 to 4 days. But anyway, do the best you can with that, okay? Remember, you won't be getting all these problems right, especially at first, okay? But you will grow throughout this review. We'll start getting topic specific, okay, in the next lesson that we do. Actually break it down for part 2 types of problems. Then we'll finish things up with some more part 1s, and then we'll focus more on what you might see on your AP. I'll try to predict. Anyway, that's all we have for today, okay? So I hope everybody is safe and healthy out there, and we'll see you tomorrow. Adios.